Hello everyone, this is Dr. Vivek Laha and you are watching my YouTube channel on mathematical magics. Today we are going to discuss about the equivalence between a basic feasible solution and an extreme point of the feasible region in a linear programming problem. A linear programming problem in its standard matrix form is given by maximization of z equal to c transpose x subject to ax equal to b and x is greater than equal to 0, where c and x are column vectors in Rn, A is a m by n matrix and b is a column vector in Rm. The feasible region of the LPP is given by all the vectors in Rn which satisfies the equality constraints and the non-negativity constraints. If the rank of A is equal to m, which is less than or equal to n, then the m decision variables of x associated with the m linearly independent columns of A are known as basic variables, and the remaining n minus m decision variables of x are called non-basic variables. The feasible solution obtained by equating the non-basic variables to 0 is called a basic feasible solution. If in a basic feasible solution at least one of the basic variables is also 0, then it is known as degenerate basic feasible solution. A feasible solution is said to be an extreme point of the feasible region if and only if there does not exist y and z in F with y is not equal to z such that x is equal to lambda y plus 1 minus lambda z for some lambda in the open interval 0 to 1. That is, if the feasible solution cannot be written as a convex combination of two distinct feasible solutions, then it is known as the extreme point or corner point of the feasible region. We may characterize a basic feasible solution by an extreme point of the feasible region. Let X be a feasible solution of the linear programming problem. Then X is a basic feasible solution if and only if X is an extreme point of the feasible region. The proof of part 1 depends on the method of contradiction. Let X be a basic feasible solution of the linear programming problem. Suppose to the contrary that X is not an extreme point of the feasible region. Then there exist two distinct feasible solutions y and z such that X can be written as convex combination of y and z. Without loss of generality, we may assume that the first p components of X are strictly positive and the remaining n minus p components of X are equal to 0. Since y and z satisfy the non-negativity constraint and y and z are distinct, therefore the first p components of y and the first p components of z will be strictly greater than 0 and the remaining n minus p components of both y and z will be equal to 0. By the feasibility of y and z, summation yiai where I equal to 1 to p is equal to b and summation ziai for I equal to 1 to p is equal to b, which implies that summation yi minus ziai where I equal to 1 to p is equal to 0. Since the p columns of the coefficient matrix A associated with the p basic variables are linearly independent, it follows that y1 equal to z1, y2 equal to z2 and yp equal to zp. That is, y is equal to z, which is a contradiction to the fact that y is not equal to z, that is, y and z are distinct feasible solutions. Hence, X is an extreme point of the feasible region F. For the other part of the proof, let X be an extreme point with first p components strictly positive and remaining n minus p components equal to 0. Then summation xi ai is equal to b. We have to show that A1, A2 to AP are linearly independent. Suppose there exists alpha 1, alpha 2 to alpha p, not all 0, such that summation alpha I equal to 1 to p is equal to 0. Now choose epsilon as minimum of mod xi upon alpha I such that mod of alpha I is not equal to 0 from I greater than equal to 1 and less than equal to p. By the choice of epsilon, we have summation yiai equal to b and summation ziai equal to b, where yi is equal to xi plus epsilon alpha I, which is greater than equal to 0, and zi is equal to xi minus epsilon alpha I, which is greater than equal to 0. Hence Y and Z are also feasible solutions of the linear programming problem. It is easy to see that X is equal to Y plus Z by 2. That is, X can be written as convex combination of Y and Z. But X is an extreme point of the feasible region. Y and Z must be equal, which implies that all the p scalars are equal to 0. Therefore, the p columns of the coefficient matrix are linearly independent and hence X is a basic feasible solution. This completes the proof of part 2. Thank you for watching. You may like, share and subscribe for more upcoming videos. Keep on smiling and spreading happiness. Goodbye.